physics time, we're talking about Newton's third law. State Newton's third law for me, someone.
Can I watch the kids?
State Newton's third law for me.
Whenever one object exerts a force on a second object, the second object exerts an unequal and opposite force on the first object.
Perfect. We sometimes say this as, I'll give you the sentence frame, for every, or do the rest. For every action,
There is an opposite equal reaction.
there is an equal and opposite reaction. I'm going to underline some things in this. Really, the one you said, Haley, is better. When an object exerts a force on another object, the second object exerts the same force back on the first, right? But this is what is classically, in fact, this is very similar to the way that Newton phrased it, except in Latin, in his Principia Mathematica when he published this. But so I'm going to learn what these things first: action and reaction. In the sentence, it is differentiated. I'm going to switch this to picture-in-picture. Yes.
After we're done, and in that thing that says in the lab that says I heart chemistry, and I know Hannah wrote it, can I put below I heart physics?
Yes, that would be fine. Thank you. I'm trying to regain my train of thought now. Okay, this is the way it's written. This is the way we commonly understand it. But these two things, really, the action and reaction are actually happening at one time, right? They happen immediately at the same time. We sometimes call this an interaction. You're aware of the word interaction, right? You might have an interaction with your cat in the morning, right? You might interact with the stairs. Anytime you are, doing something with another thing, that is an interaction. And we use that same word for these forces. The two things interact. If I push on this whiteboard, which I'm doing, if I push on the whiteboard, then what?
Who's pushing back?
The whiteboard is pushing back. In fact, a really easy way to do these when we get to like the non-mathematical side of things, when we talk about the problems, if A acts on B, then what?
It
B
will push.
acts
Yeah, it's
on
on
A.
A.
So if I kick the soccer ball
Well,
say it.
Kicks back.
Yeah, kicks me, right? The soccer ball kicks me back, right? We just got done talking about this in 8th grade science last week, and we did a unit on collisions, and I said when your phone breaks, it is not your phone hitting the floor that breaks the phone, it's what?
it's the
Floor.
Yeah, the floor hitting the phone, right? When the boxer breaks his knuckles on the other boxer's jaw, it's not that he hit that guy, it's that the guy's jaw hit him back, right? So if A acts on B, then B acts on A. Very importantly, and almost, I wouldn't say confusingly, but people have a lot of misconceptions about this, with the exact same force. So this is where it gets, like I said, not confusing, but people have a lot of misconceptions about this. So make sure you pay attention to the physics of it and not try to get too wrapped up in what you had previously understood, right? So first of all, if I push this wall, I can push it hard enough that I bounce back, right?
Mm-hmm.
Why do I move and the wall doesn't? So first of all, let's think about just...
Unbalanced?
Exactly. So let's think about just the wall. So just the wall, in this interaction, just the wall, what force is acting on it? So, okay, there's gravity acting on the wall for sure. F sub g. What else? Maybe not for the wall. Yeah, the force I'm pushing on with, I'm going to say it's this way, the force of the push.
And isn't the floor pushing?
Yeah, there's some normal force, right? There's some support force, which since it's still, we know it must be acting to the same magnitude as gravity. And then what else? Well, there's also some support force acting in the opposite direction. I don't know what it is exactly, but somewhere there's a beam or some nails or screws that are holding this wall in place. In fact, it's brick on the other side, so it's bricks and mortar, right? The structural integrity of that is exerting a force back on me. Now, thinking about me, I'm going to draw this picture of this idiot. Thinking about me, what forces are acting on me in this case? Gravity. I have a certain weight. We'll make it less than the weight of the wall, I hope.
The force of the wall pushing onto you.
The force of the wall pushing back, which must be what? How is that related to this push force?
It's the exact same.
The exact same, but the exact same magnitude, but in the opposite direction. So it has to be the exact same length I don't, oops, that should be an F, not a P. I don't think I probably pushed harder than what I weighed, but that's what I've drawn it as. These forces are unbalanced. What else is balancing the force of gravity?
Something pushing.
Yeah,
Pushing against the wall.
The normal force from
Yeah.
the floor. And then is there anything balancing the push force?
Well, you're pushing.
Maybe not balancing, but is there anything resisting the push force?
Friction?
Friction, a little bit of friction, right? The fact that I moved means that there's less friction than the push force, right? So all these forces are acting on me. But the important thing here is that it's the exact same force acting except in opposite directions. So here we go. Now that we've drawn this, here's the first common misconception we encounter. Why don't these forces, these meaning action and reaction, why don't they cancel? Right? They're the same, and in the opposite direction. Why don't they cancel? So we have this force here. I'm going to highlight it in a different color.
Because one's balanced and one's unbalanced. So that means that they...
Okay, that's true, but that's not why they don't cancel. What did you say, Taylor? Oh, nothing. What did you say, Hannah? Sorry.
I didn't say anything.
Oh. Did you say something again? Maybe I just heard you think. They should be, I tried to draw them, equal in magnitude but opposite in direction. Why aren't they balancing? This is I think you might be making it too difficult. Why aren't they balancing each other out?
Like canceling each other?
Yeah, why aren't they canceling each other out?
I don't know.
Is it like, I'm not saying mass, but I think so.
Equilibrium.
This one is in equilibrium. What is balancing this force that's making the wall not move? We said that some other support force, right? So this one is balanced, but it's not balanced by this. Why? They're acting on what?
They're acting on an object that is still or in rest.
News first law.
They're acting on different objects, right? They can't balance because they're acting on whole different things. I'm different from the wall. The forces don't balance, so write this down. This is, hopefully you understand what I'm talking about. They act on different objects. They act on different objects. So once again, maybe it'll make it easier if I draw that, first of all. Maybe it'll make it easier if I completely erase me.
So it'd be different, the wall is pushing on itself.
Right, yeah, it doesn't balance because there's no force balancing it. If we look at just one object, it doesn't balance itself because it's not on one object. They're on separate objects. They act on different objects, right? One force acts on me, the other force acts on the wall, so they can't balance because they're acting on separate objects. Oh, here, I just did this. I didn't mean for it to be an example, I was just getting it out of my way. But if I do this, what happened there?
It bounced back.
It fell. The bottle fell. Here's the bottle. It fell. So what force was acting on it?
Gravity.
From what?
From the point it was dropped.
I mean, what provided the gravity that caused this to fall?
The object's mass, right? Or,
Yeah, the attraction between the object's mass or weight and the,
Well,
not just the floor, the whole what? What's attracting this down?
everything.
What's providing the gravity?
um,
What's down here?
the core.
The earth, the whole dang earth, right? Gravity from the earth. So the bottle, let's phrase it this way. Earth pulls on the bottle, right? So using our little sentence frame, what else happens? Say it. It doesn't sound right, but say it. Earth pulls on the bottle, so
The bottle pulls on
the bottle pulls on the earth. Does it?
Yeah.
So here's the second misconception. It does. We know it does. According to this third law, it has to, right? But the misconception is, well, it doesn't seem like it does, right? So what are we actually looking at? Are we looking at the force? When we're talking about, well, what two things, as we just talked about yesterday, does force depend on?
Mass.
Yes? So we have force equals mass times acceleration. So when we're thinking about the bottle falling, are we really looking at the force on the bottle, or what's it doing that we're really observing? It's accelerating, right? We're observing its acceleration. So just because we don't see the Earth accelerating up to meet it, does that mean there's no force acting on the Earth? No. So basically, how do we know these two forces? Here's Earth, here's the bottle. This is I don't know, I was going to say better, but not necessarily. Just a different drawing. We know there's a force of gravity acting on the bottle from the Earth, right? What else must there be?
Force acting
Yeah. There's some force pulling the Earth up towards the bottle. So why don't we notice that force? Well, look at this. What's different about the bottle and the Earth? Do they have different forces acting on them? No, it's the same exact force. What's different about them?
Mass.
This is a dumb question, is there a difference in mass between planet Earth and this little whiteboard erase bottle? Yeah, of course there is. So let's do it this way. The forces must be the same, right? We know the forces have to be the same, so I'm going to draw those the same size. Let's put this, force of Earth and force on the bottle. So the force on the Earth equals what? Times what?
And mass and acceleration.
Yeah, the mass of the Earth times the acceleration. What's the Earth's mass like compared to the mass of the bottle? This is a dumb question too. Much larger. So I'm going to draw a great big. Great big mass of the Earth. And for the bottle, compared to the Earth? Little baby. Mass of the bottle is little baby. So therefore, what must the accelerations be like to balance it out? If the force has to be the same, which we know it does, then what must the accelerations be like?
Small and big.
Yeah, so small on the Earth, little baby acceleration on the Earth, and great big, I'm kind of invading my other spot, great big acceleration on the bottle. That's why we notice a difference in the bottle's velocity, but we don't notice a difference in the Earth's velocity. Is it true that the Earth is technically accelerating towards the bottle? Yeah, but by the time the bottle hits, it has accelerated, because it has such a huge mass. Oops. Since it has such a huge mass, it's accelerated so little it doesn't even move an atom. It doesn't move at all, right? It technically moves, but we could never measure that movement because the force is the same, but the acceleration of the Earth is so tiny, right? Don't get tripped up. On your test, there's going to be all kinds of questions like this. Remember this in your head above all the things. No matter what seems right based on your intuition or your gut instinct, remember that the force of the action is equal and opposite to the force of the reaction. Both forces have to be the same. It is a law. It is a Newton's law. It's a Newton's third law. Think about it this way. I'm going to erase some of this. I'm going to erase most of this. Do you have questions about that before I go on? So just those three quantities. Thinking about, let's do it in a different example. If we have, I'm going to draw this on the board in a second, but if we have a gun firing a bullet, it's like deer hunting season. You guys know about deer hunting? Have you ever hunted a deer?
Yeah.
Raise your hand if you have fired a firearm.
A Nerf gun.
That'll count. A Nerf gun will count. That's not. It doesn't count as a firearm, but it does count for this example. So I'm going to draw a gun.
Oh.
This is what it looks like to me. This is going to be a good gun, actually.
Well, that is good. Put a scope on it.
Oh yeah, we got to get a nice dang scope on here. There we go.
Trigger.
It's got iron sights too, in case you want to take the scope off. Anyway, so there. Oh, it's got to have a grip. Okay. Nice. Ooh, yeah, that's good. Okay, so this is a cross-sectional view of our firearm. When it fires, there's a bullet inside of it, right? There's a cartridge. This is not the point of this class, but you should be aware that the cartridge, the thing that you put in the bullet, is called a cartridge, and then the thing you put in the gun is called a cartridge, and the bullet is only this little like front part that flies off, right? The rest of it is spent. Anyway, so.
Doesn't it spin in it?
Yeah, it does. There's what's called rifling in here. This is not gun class, but anyway, there's rifling in there that makes the bullet spin, which affects its trajectory. Anyway, when the gun is fired, right, there's an explosion inside. Force of the bullet on the gun and force of the gun on the bullet. Let's talk about that. So force, what do we know about the forces? They must be equal. So force on the gun and force on the bullet. This is the same exact thing as that Earth problem, you see? So what's the mass of the gun like compared to the mass of the bullet? Bigger. Significantly larger, right? So once again, mass of gun is bigger, mass of bullet smaller, and therefore,
Accelerations are opposite.
right? In this case though, and this should still be a lowercase a, in this case though, and this should say bullet, I'm sorry, I'm just really a really big mess of this. In this case though, unlike the Earth and bottle example, we do notice an acceleration of the gun, don't we? It's small, but it's noticeable. How do you notice it? What does it feel like?
I don't know.
Yeah, it feels like recoil, right? It feels like it hits you in the shoulder. I guess if you're left-handed, it hits you. Who's left-handed? Oh, Hannah. That's why you pointed to your left-handed shoulder. Left shoulder, you might even call it. No one calls it left-handed shoulder. Whatever. Anyway, you do notice the acceleration of the gun, unlike in our earth and bottle problem, right? So there's going to be a question in chapter review that says, Tommy, or some other name, Tommy has a good idea to get more firepower in his cannon. He's going to use a cannonball that has the same mass as his cannon. Is this a good idea or not? Why is it not a good idea?
Because the acceleration is going to be smaller.
Right. Well,
Or like equal.
It's going to be a heavier mass.
The cannonball will not accelerate as much. But furthermore, why else is it a bad idea, right? If we've got, here's the cannon, here's Tommy. We're going to draw him with a dumb face. And here's the cannonball. What's going to happen when Tommy lights the cannon? It's going to accelerate. Both of them will accelerate to the same degree, right? Because they have the same force,
Poor Tommy,
right? They have the same mass, and therefore the same acceleration. And so it's going to hit him just as hard as whatever he's aiming at. Right. His legs will be taken off, right? He's going to have no legs pretty soon. So no, Tommy, that's not a good idea. The last thing I think that I want to talk about that your book mentions, there's a lot more stuff in here. You definitely need to read this. There's a whole section called the horse cart problem, which is a cartoon.
I already read it.
Good. It's kind of good, isn't it? Yeah, she says good.
And then all of them, and I read another one, and then they're like, physics.
Yeah, they do.
Yeah.
They think physics. The other thing we need to talk about real quick is this. I'm gonna try.
I just brought more.
Mr. Snitley always tells me. He says, "Be really careful when you're drawing rockets in class." I don't know what he's talking about. Anyway, so here's a rocket. When the rocket is being fired.
Flames.
Oh yeah. Well, that's what we're gonna draw in a second. When the rocket is being fired, what? What happens? What's coming out of it?
Explosion.
Yeah, it accelerates up because what? This is stuff, right? Even though, like, if you were to touch this, it would be hot. But if you were to touch it, it looks like a cloud, and it would probably feel like a dense cloud, but it would also melt your fingers. But this is still matter, right? It's ejecting matter. And so the force that the rocket is putting on the gas, force of rocket on gas, my marker's kind of dying, force of the rocket on the gas must be what? What must the gas do? According to Newton's third law. If the rocket's putting a force on the gas to get rid of it,
must give a force.
the gas puts a force out, right? In fact, this is why we use rockets in space. I don't know if you've ever wondered, why don't we just fly a plane into space? Well, a plane has a different operating mechanism. Basically, the rocket works because it's constantly emitting gas. How could you move in space? If you were stranded in space, dying because you're in space, what could you do to float yourself back to the space shuttle? Could you swim? No, because there's nothing to push against, right?
Emit gas.
You could emit gas. You could emit anything, really. You could emit anything. Hopefully your bladder is full because you could just pee your way back to the spaceship. That's inappropriate, but true, right? You have to be able to emit some matter, right? If you can't emit matter, what could you do? Like realistically, this happens, I think, in a Roald Dahl book. I remember, like the second Charlie and the Chocolate Factory. They're in outer space. How can he move from one side of the room to the other? He blows. And then it like gently blows him backward, right?
The fizzy lifting drinks.
Yeah. Have you read the second Charlie and the Chocolate Factory?
I've never read it, but I watched the movies.
Okay. Yeah. Anyway, so that's how a rocket works.
I think the second movie-
It puts a force on some matter, and then the matter puts the force back on it, which causes it to propel. Do you have questions about any of this?
No.
Okay.
Can I